So we have the Graph 1 worksheet. The following table contains data representing the motion of a person running. So we're going to graph the displacement and the time based on the table given. So you can see I'm already building my scatter plot. With the time at 1 second, we've got a distance of 12 meters, 2 seconds 19, 3 seconds 26, 4 33, 540, 645, 754, 8 seconds at 61 meters, 9 seconds at 70 meters, and 10 seconds at 75 meters. Once I get those plotted, we're going to draw a best fit line. Now, a best fit line is not going to be forced through the origin. It's going to be a line that best represents all of the data. Now, when I draw my line, I don't have a ruler with me when I'm doing this. I'm doing it electronically, but you're going to want to use a ruler, line it up so it has the same trend as the data, the same slope, and then slide it right into the middle of everything and draw the line all the way through. Go beyond the graph, and as far as you can go on both sides, it's going to be your best fit line. Don't force it through the origin. Don't force it through any points. I would have liked my line to be a little bit lower, but I don't hate it. I can kind of accept where it is. The next thing we want to do is find the slope of the best fit line. I'm not going to use any of the coordinate points for the slope. What I'm going to do is find where my line either goes through the crossing point of my grid or the midline between crossing points, because I can best determine the coordinates of those two new independent points, not from the table. Maybe if it happened to just go directly through the center of a point from the table, maybe you'd use it, but generally let's try to avoid that. Once I have those 2 points, we're looking at the change in y over the change in x, or if you prefer, rise over run. I've got 2 points. I'm using my x coordinate, or my y coordinate is 60, x is 7.5, and then when the y is 30, the x is 3.5. Do the subtraction and then the division, and let's see what I get. 30 divided by 4, it looks like. Handy dandy calculator. And I get 7.5. Now it is rise over run, so the units of the rise was meters and the units of the run was seconds, so it'd be meters over second. So 7.5 meters per second would be the velocity of my runner. What information about the runner does the slope of the line yield? Well, it's a constant slope. The slope's not changing. It's a straight line. So if it's a constant slope, it's a constant velocity, because we're getting the velocity meters per second. That's the unit of velocity. And if that slope is constant, so is the velocity. If we check the slope at any point in the line, it is going to be the same. What is the significance of the y-intercept? What does it mean for the runner? Well, the y-intercept is where the runner is at when the time point is 0. When the time point is 0, where is your runner? Now, if it's at the origin, if the line hits the origin, well, then the runner is at the origin, it's at point 0. But in this case, our runner was not at the origin. So our runner's starting point was actually ahead. He wasn't in zero negative territory. He was ahead, and we'll determine that in one of the follow-up questions is, where was this runner at the start of the race? And if you've ever been to a 5K, or if you've ever run a race, if you've seen one on TV, you'll see that when the race starts, there's a couple of people in the starting line, but many people are further back. In this case, this runner was already ahead. Let's get this fully written out, and then we'll be ready for the next question. So in this case, it means the runner had a head start because they were in positive territory. It's just a way to interpret the graph. Being able to look at a graph and make up a story in your head so that you can answer questions based on your knowledge of what's going on. What is the runner's position after 12 seconds? Well, if we know where the runner started and we know how fast the runner's going, we can determine where they're going to be in 12 seconds. We're going to start with our equation. The x position is equal to velocity times time plus the initial x position. So that head start will affect things. So x equals vt plus x naught. Well, what do we know? Well, we know the velocity is 7.5. And we know the time is 12. They gave that to us in the problem. And the velocity being 7.5, that came from the previous problem. We're looking for x, but we don't really know what x naught is. We don't know what the starting position. And yes, you can look at some graphs and you can kind of guess, but if each vertical line or each horizontal line going up vertically is worth 10, it's really hard to estimate. So if we use y equals mx plus b, we could solve for b because b is that x naught. Now in the y equals mx plus b, the y and the x can come from coordinates that we use to calculate the slope. We had a coordinate of 3.5, 30. 3.5 is the x, 30 is the y, and then the slope, the m, is 7.5. We can use that to solve for b, and that gives us our x naught, our starting point, our y-intercept, in this case 3.75. We're being a little bit more accurate through the calculations, and I doubt we could have looked at that line and said, oh, that's obviously 3.75. Now that we have it, let's put it back into our equation. We have x is equal to vt, v is 7.5, t is 12, plus the initial position of 3.75. Do the math, we get an x position of 93, it should be 93 meters, or I'm sorry, 93.75 meters, because displacement is in meters. What is the runner's position after 16 seconds? Same setup. Our position is equal to the velocity times the time that we've been traveling that velocity, plus any head start that we had, right? So if x is what we're looking for, v we know is 7.5, t in this case is 16 from the problem, and our initial position is still the 3.75 that we calculated previously. Let's put it all together. X is equal to 7.5 times 16 plus the head start of 3.75. Doesn't that make sense too, though? I mean, if you have a further head start, you're going to be further out. If you started at 0, you wouldn't be as far out. So we have to account for all of those things. And we know displacement is velocity times time. That's something that we've seen in other places. All right, let's go to the back page now. Now we have a velocity versus time graph. It's not a displacement graph, it's a velocity times time graph. They're telling us that they maintain the same velocity for 0.6 seconds. So we're going to just say the velocity was 0.5 for 0.6 seconds. And then it took 0.4 seconds to slow down to a stop. Well, where's a stop on the velocity graph? It'd be a velocity is equal to 0, right? So it's going to take 0.4 seconds to go from where we are down to a velocity of 0. And then they're going to stay not moving or stopped for how long? Half a second, 0.5 seconds. So we're going to stay at 0 at 0.5 seconds. That gets us to the 1.5 second mark. And then it says for the next half second, we're going to be speeding up to 1.5 meters per second. So we're going to be going up to the 1.5, but it's going to take us 0.5 to get there. So we're going to be sloping up as we go. And it'll look something like this. So this is our velocity versus time graph, and it shows us how fast we were going for any given moment in time. This is not a displacement graph. As we hit the horizontal axis in a velocity graph, our velocity is 0. If our slope is 0, it means a constant velocity because the velocity value is not changing. So those two 0 slopes, that just means whatever velocity is marked, 0 slope is 0 change in velocity because it's maintaining that same value. Find the slope of the line for each one. So we've marked the 0 slopes. Now we just need to calculate 2 of them. So from 0.6 to 1, we're going down, so rise over run, but the rise is a drop of negative 0.5 divided by 0.4. So negative 1.25. The slope being rise over run, so meters per second or meters per second square. The other one we need to calculate is from 0.5 to 2. Here we're rising, the change in y is 1.5, and then the run is 0.5. So 1.5 divided by 0.5, and there we get 3 meters per second square. What does the slope represent? It's acceleration. It's a change of velocity over time, which is acceleration. Change of velocity is acceleration. C asks us how far does the man travel in the first 0.6 seconds? Well, how far does a man travel is displacement. And from a velocity versus time graph, displacement comes from the area under the curve. So what I really like to do with area under curve is I'll shade it in so I can see what I'm looking for. I can visualize. I want to make things into either rectangles or triangles because I can calculate the area under the curve for a rectangle or a triangle. Rectangle is base times the height, triangle 1/2 base times the height. So I'm just shading all of those in because I know I'm going to be working on all of these as we go along. So the first 0.6 seconds, the height is 0.5, the width is 0.6. So we can take that 0.6 times 0.5, and that should equal 0.3 meters. And we know it's meters because it's displacement. Also, m over s times s, the s's cancel out, we're left with the m, which is meters. So 0.3 meters. Find the area under the graph for the interval find the interval from 0 seconds to 0.6 seconds. That's what we just did. We have that answer, 0.3 meters. What are the units of this area? Again, meters. And what does the area under the graph represent? Displacement. We're smart enough. We already figured those things out. Let's add on, how far does the man travel in the first second? So now they're saying from time point 0 all the way to time point 1 second. Well, we've already calculated the first 0.6 seconds. Now we need to just calculate from 0.6 to 1. So in the first 0.6 we had 0.3, and then from 0.6 to 1 we'll have 1/2 the base times the height. So 1/2 times 0.4 times 0.5. Put that into our handy dandy little calculator. .4 meters. How far does the man travel overall? Well, we've already calculated up to 1 second, and we know he's not moving from 1 to 1.5, so now we just add in that triangle on the far right from 1.5 to 2. So we've got our 0.4 plus 1/2 times 0.5 times 1.5, because the triangle is 1/2 the base times the height. And then, of course, we're adding in the 0.4 that we calculated for the first second, and we should get 0.775 meters.